Hello, welcome to lesson 11.3 on circular and periodic functions. Today we're going to be talking about something that is called the unit circle. Now, this is what I think is probably one of the most important topics in math. It connects things that are seemingly very, very far apart from our kind of assumptions. So, the things that it connects specifically is it connects the shape of a triangle to the shape of a circle. Okay, those two things are not obviously connected. It even goes further than that. It connects the shape of a triangle to the shape of a wave. Okay, so it provides us a way of understanding waves in nature, things that kind of go up and down and up and down, things that change periodically, which could be tons of things. It could be the populations of animals in the wild, could be the temperatures of the earth as the different seasons go by, could be the vibrations of molecules or the wavelengths of atoms. There's tons of things that are described as waves in nature, and we're going to kind of get the tool that's going to allow us to approach that stuff. Okay, so that tool is called the unit circle, and that is what this lesson is mainly going to be about. Let's go ahead and look on here real quick. So today's goals in general, as stated in the chapter, are to find values of trigonometric functions given a point on a unit circle, or by giving the measure of a special angle. Okay, so just to kind of jump to the punchline here, what they're referring to as special angles would be any multiple of 30, 60, 90, 120, 150, 180, 210, 240, 300, 330, and multiples of 45. So 45, 90, 135, 225, and 315. So those are, you're going to kind of come to see those are what's known as special angles. If you'd seen my video, my previous lesson video, I talked a little bit about where those special angles come from. So the 30s and the 60s come from a 30, 60, 90 triangle, a triangle that has the angles 30, 60, and 90 in it. It really just comes from an equilateral triangle that's been cut in half. So if you kind of pick some numbers here, so for example, I'm just going to pick 2 for the side length of my equilateral triangle, so 2, 2, 2 on all sides. Well, the bottom that got cut in half is 1, and using Pythagorean theorem, we would know that this side squared plus this side squared needs to equal this side squared. So 1 squared is 1, square root of 3 squared is 3, and together they make 4, which is 2 squared. So all three of those work out. And you can get that by just starting with an equilateral triangle and cutting it in half. The second special angle is the 45-degree angle. When you have a 45-degree angle in a right triangle, the other angle that is not the 90 will also be 45, so they all add up to 180. And if those two angles are the same, then we will get two side lengths that are the same here and here. So once again, just picking a number, 1 and 1, would mean that this number would have to be the square root of 2, right? 1 squared plus 1 squared would be 2, and square root of 2 squared would be 2. The sum of these squares needs to equal this square of the hypotenuse. Okay, so these are the two special triangles. That's really all you need to get started approaching what we're going to call special angles, which you'll see a lot of. You just kind of have to have an understanding of these two triangles. Now, these numbers here can be changed. So, for example, I could double all of these. I could make it 2, 4, and 2 square roots of 3. I could cut them in half. I could say 1/2, 1, and root 3 over 2. Okay, so I can make these triangles bigger or smaller, however much we want. But this is just kind of the basic one that we usually reference off of, with a side length of 2 up here, 1 square root of 3, side lengths of 1 and square root of 2 on this one. But we will see how we're going to actually kind of change those to a different scale when we're using our unit circle. But we'll get to that in a moment. Okay, we also want to be able to find values of trigonometric functions that model periodic events. So periodic means like repeating over and over. You can think of like if you're do any music, like a metronome that's kind of going back and forth, tick, 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 tick. That would be a periodic event, something that's repeating over and over. Today's vocabulary, most important, is this unit circle, this tool that we're going to use. We're also going to talk about circular functions, periodic functions, cycles, and periods. Okay, so let's start with that circular function. A unit circle is a circle with a radius of 1 unit. Okay, so that's all it is. It's just a circle that has a radius of 1. So on the right side, we're at 1, 0. On the left side, we're at negative 1, 0. Up above, we're at 0, 1. Down below, we're at 0, negative 1. So we're just talking about a circle that has a radius of 1. If we go to like an interactive unit circle, this is a circle with a radius of 1. So no matter where I move my mouse, the gray line that forms the hypotenuse of this right triangle has a length of 1. Okay, and that's very important, and that's going to come in and kind of mix with our trig ratio ideas in a really helpful way that we'll see soon. So if I kind of jumping around here. If I wanted to think about my drawing here, which is my unit circle, which always has a radius of 1, what's going to be a little bit more helpful than having these particular triangles is going to be having triangles that have a hypotenuse of 1 so that I can imagine them being in my unit circle. So for example, if I go to like 60 degrees, the only difference between this one, where the blue line on the bottom says 0.5, and my triangle I drew that has 1 on the bottom, is that this triangle is half as big. So that's what we want to do with these. We want to make these two half, we want to make this one half as big, right? So for this one, we want to have the radius, the hypotenuse here be 1 so that it can fit into our unit circle, which means that this needs to be half as big, so 1/2, and this needs to be half as big, so √3 divided by 2. Now, when we look at our other special triangle, this one actually needs to get changed in a different way. So just the way that I would express this is that the change that we're going to have to do to get from here to here, well, first we're going to have to multiply by square root of 2, okay, to get rid of the square root symbol. That will make it 2, and then we're going to have to divide by 2. Okay, so that it comes back down to 1. If we follow the same proportion with each of these, multiplying by the square root of 2 and dividing by 2, then we will get our special 45-degree triangle written out at a scale where the hypotenuse is 1, and we can put it into our unit circle. So evidently based off this, they don't give us fractions with radicals in it. They just give you the decimal. So square root of 2 divided by 2 apparently is 0.707. Okay, let's move on with what they're saying out of the book. The unit circle has a radius of 1 unit and the origin on the coordinate plane. Sorry, centered at the origin on the coordinate plane. So the center of the circle is at the origin. Notice that on the unit circle, the radian measure of the central angle equals s over 1. Okay, so let's break that down a little bit. The radian measure of the central angle. So first of all, they're saying the unit circle, we typically want to do it in radians. Now, we will see it with degrees sometimes. So like on here, you can put on degrees around the outside of your circle, 30, 45, 60, 90, or you can switch it to radians, where we have like pi radians over here. We have 2 pi radians when we go all the way around. Therefore, we have pi over 2 at that position. And these are all fractions of pi radians. Okay, so we will probably get used to it a little bit, starting with degrees, since that's what we're generally more familiar with. But the end goal is to get it where we're looking at this in terms of the radians. Okay, now, so it says the measure of the central angle equals s over 1. So I think I've shown you an image of that before. Let me look it up one more time. Where they kind of describe what the definition of a radian is. And it's basically, so there's a little GIF that shows it, but in case I don't find that, I'll just kind of bring this one up. A radian is the angle that makes it so that the arc length, the length around the circle from here to here, is the same distance as the radius. So you've got some radius, which in our unit circle, remember our radius is 1, which means that at 1 radian of angle, this arc length should also be 1. Okay, so that's kind of what they're getting at in the book right there. I like it. It's not popping up. Okay, we'll move on. Okay, so the radian measure of an angle is the length of the arc on the unit circle subtended by the angle. Okay, so the radian measure of an angle is the length of the arc. So they're basically saying that if we have, if we want to find this arc length, typically the way that we do it is we take our angle and multiply by our radius. So what they're saying is in the unit circle, where the radius is 1, our arc length and our angle will always match in value. So, for example, let's play that out real quick. If I am thinking in radians, where I have pi radians and I have 2 pi radians when I go all the way around, what they're saying is that if I, for example, have an angle of 90 degrees, then I should have, when I change that into radians, the corresponding match would be pi over 2 radians. And that will also be the length around the circle. That'll be the arc length from here to here. So if we go over to pi radians, then we'll have an arc that is pi in size. And if we go to 2 pi radians all the way around the circle, we will have a circumference of 2 pi. Well, our circumference, we already know our circumference formula, hopefully. That's 2 pi times the radius. If the radius is 1, we would expect for the circumference to be 2 pi. It'd just be 2 pi times 1. Okay, so they're saying that on the unit circle, in summary here, whatever angle we're talking about in radians, let's see if I can change this so that, do they give it where we can do it in radians? Not sure that they do. Whatever the angle is in radians is also the arc length. Okay, those will be identical on the unit circle. Okay, so this angle here will be the same number as this arc length. You can use a point P on the unit circle to generalize sine and cosine functions by applying the definitions of trigonometric functions in right triangles. So what they mean there is once you have a point on your unit circle, so for example, let's go to the point, well, they're not recording the point here. Okay, let me think of a different way to say this. The point right here, like the coordinate of the little dot where my mouse would be 0.5, comma 0.866. Okay, that would be the actual location on the graph. It would be at 0.5 on the x-axis and 0.866 on the y-axis. That should make sense. That's the that is the 0.5 is the distance in the x direction, and 0.866 is the distance in the y direction. So that's where the coordinate should be. Now, if you want to know what the sine of this particular angle is, the sine is also going to be 0.866, right? Your sine is your opposite side divided by your hypotenuse. So for that little right triangle below my mouse, the opposite side to that angle is the green line, and the hypotenuse is the gray line. But the hypotenuse is 1, right? We're in a unit circle. We have a radius of 1. So when we look for that ratio, when we look for that trigonomic ratio of the sine ratio, opposite divided by hypotenuse, we basically get the same thing as if we just looked for the opposite side. So that means that what these two values will tell you, the coordinate position, so in this case 0.5, 0.866, what these two values will tell you, let me add it to my drawing over here, they will tell you what the sine and cosine of your angle are. So for example, if I go to, let's go to 30 degrees. So our coordinate should be 0.866, comma 0.5. Okay, so if I wanted to add that coordinate on here, it's 0.866, comma 0.5. And that is for this angle right here. Now, what that's actually telling us is that the sine, sorry, make sure I say this in the right order. 0.866 was our x value, so that would be our cosine. And this would be our sine. Okay, so that's just generally what the points along the outside of the unit circle tell you. you'll have two coordinates, like anything on the coordinate plane. You'll have an x coordinate, where we are right here. And in this case, that was 0.866. And you'll have a y coordinate, so like where we are right here. And in this case, that was 0.5, halfway up, which looks about right to me. Okay, and those two values are the cosine of the angle and the sine of the angle, right? Because for sine, we're talking about the opposite side, which is our height here, 0.5, divided by the hypotenuse. Hypotenuse is just 1, so this number doesn't change. Okay, so this is the beauty of the unit circle. It packs a whole bunch of information all together. In the coordinates along the outside, it tells us the cosine and sine of whatever angle points us to that coordinate. It also tells us something about the arc length. The arc length around that circle will be equivalent to the angle itself. So if my angle is going to be, let me do this one in radians real quick so we get some more practice here. If my angle is, well, we have pi radians at 180, pi over 2. This is a third of that, so that should be pi over 6. So if I have an angle that is pi over 6 radians, I will have an arc that is pi over 6 units long. Okay, so there's a lot of connections. We can connect the length of the side of a sector here with the angle that produces it. We can connect the angles to the sine and cosine based off the coordinate that we get along the outside. There's a lot of different things that come out of this unit circle, which makes it a very, very handy tool. Okay, so it says that you can use a point P on the circle to generalize sine and cosine functions by applying the definitions of trigonometric functions. That's what we just kind of talked through. Okay, so here, if the terminal side of an angle in standard position intersects the unit circle at some point xy, so we're here at xy, then this is just what I said a moment ago. Your x coordinate will be the cosine of that angle, and your y coordinate will be the sine of that angle. Okay, so that point gives you that information of cosine and sine because we're always just dividing by the hypotenuse for those two functions, and that hypotenuse is 1 no matter where we put our right triangle. So it's just those two values, that green value and that blue value, those x and y coordinates, that tell us what our sine and our cosine are going to be. So in this example, they say their angle they're going to use is past, pi radians. It's 5/4 pi, a little beyond 1 pi radian. So we're over here. The two coordinates are going to be the cosine of 5 pi over 4 and the sine of 5 pi over 4. Okay, so we can locate ourselves around that circle using that connection. Both cosine of theta equals x and sine of theta equals y are functions of theta. So our input, our variable, is the angle. Because they are defined using a unit circle, they're called circular functions. Okay, so this cosine and this sine thing are called circular functions, which describe a point on a circle as the function of an angle defined in radians. Now, where we're going to go with this is we're going to say, okay, well, how does that play out on a graph? So if I go to Desmos, well, actually, sorry, let's just do the unit circle. What I'd like you to pay attention to right now is the height of the green line under my mouse. Okay, so that height's going from 0 up, up, up to a maximum of 1, comes down to 0, goes down to a minimum of -1, comes back up to 0. Okay, that is as the angle increases. Okay, now we're going to look over here on the graph. My mouse, as I go to the right, I'm tracking the x-axis here. So I'm seeing 0, pi over 2, pi, 3 pi over 2, 2 pi. This is an increasing angle, right? We're going from 0 to 2 pi. So we're going all the way around the circle. Now, if we follow the green line, I know there's a lot going on, so just try to follow the green line here that goes up and down and up. Okay, this is the sine graph. This tells us what is the value of the sine. Well, the value of the sine, it matches what is over here on my triangle, right? So once I'm at 0.5 here, my green line is at 0.5. Once my green line is up to 0.89, 9 about, we're at 0.9 on the graph. And as I go around, this graph here, this green line that goes up and up, is tracking the progress of the height of this green line on the right triangle. It goes from 0 to 1 to 0 to -1 to 0. 0, 1, 0, -1, 0. Right? And as I continue spinning around and around and around, it just repeats. So if I type in sine of x, I get a graph that goes from 0 to 1 to 0 to -1 to 0, and then it just repeats that. So it repeats it over and over and over forever. This is what's known as periodic behavior. It's just repeating over and over and over as we increase that angle out to infinity.